So the first thing we talked about was mass spectroscopy, and I told you, okay, when you do mass spectroscopy of a molecule, uh, there is a molecule that you add in the ionization chamber, and what happens to it is, okay, it's bombarded by electrons and it ionizes, and it always forms. You're always detecting plus one ions. I mean, it forms all sorts of ions, but your instrument is targeting plus one ions. Okay, it's not that plus two ions and plus three ions and minus one, minus two ions are not being formed when the molecule gets bombarded. But your spectroscopy, your instrument is only detecting plus one ions. Uh, Now, a molecular ion would be formed like ethanoic acid. It loses one electron, it forms a molecular ion, or the molecule might break down into smaller fragments. And each one of the fragment is a piece of the original molecule. Like if it's not a piece of the original molecule, then that could not be formed. For example, over here, an O2 plus ion would not be possible. Okay, if I had written that, uh, if I had written that there was an O2 plus one ion also getting detected, that's not a possibility because in the structure there is the oxygens are not together. So anything that would be formed, a fragment that would be formed, would be a part of the original molecule. It would be a structure that would be present in the original molecule. I said, anyways, so we discussed chlorine. Yesterday we discussed chlorine, and what we discussed about chlorine was that you had a chlorine molecule. Uh, if you ionize it, you send it to the ionization chamber. What's going to happen is that a Cl2 plus one ion would be formed. That's your molecular ion. But the Cl2 molecule might also break down into smaller, tiny Cl atoms that would ionize as well. So Cl plus one fragments would also be formed. So these are the only two things that are possible in the ionization chamber. Uh, Once that happens, the beam of charged particles is passed through a magnetic field, and charged particles they get deflected. And I told you that deflection is proportional to charge over mass. It's inversely proportional to mass. Heavier particles are not going to get deflected by a large amount. Lighter particles will get deflected by a very large amount. They would face more deflection. So since the charge is constant, charge is not a factor. I mean, it's always a constant. You're only detecting plus one ions. Uh, if there were plus two ions, the deflection would be even more, which is why your detector is tuned for plus one ions, because plus two ions would probably get deflected more. So you're not even detecting them. I say anyway, so your plus one ions they get deflected. And I told you that different atoms have different isotopes. So chlorine. Now chlorine is important. The reason chlorine is important because its isotopes are very abundant. That out of every 100 chlorines, there are 25 of them which would be chlorine 37, and there would be 75 which would be chlorine 35. So the probability is 3 by 4 and 1 by 4. So the abundance of the isotope is a lot, which is why your mass spectroscopy is going to be highly affected by the different isotopes. So for example, there would be three different detections for Cl2 plus 1. There would be a Cl2 plus 1 that would be 74. There would be a Cl2 plus 1 that would be 72, and a Cl2 plus 1 that would be 70. Why? Because either both chlorines are 37, or one of them is 37, the other one is 35, or both of them are 35. So you're going to get three different masses of the Cl2 plus 1 ion. Plus, you're going to get the fragments as well. Those are lighter, so they're deflected more. So you're going to get a deflection at 37 and 35 as well. And then we calculated the probability of getting these particles. What's the probability of getting both of them as 37? That's 1 by 4 into 1 by 4. That's 1 by 16. What's the probability of getting both of them 35 in the molecule? So that's 3 by 4 into 3 by 4, which comes out to be 9 by 16. And what's the probability of getting 72? That one of them is 35, the other one is 37. Or the first one is 37 and the second one is 35. So calculating the probability, we got 6 by 16. And so probability wise, if you had 16 occurrences, nine of them would be nine times you would be getting 70. Six times you'll be getting this molecule which has a mass of 72, and only one time you'll be getting this molecule which would be 74. So the relative abundance of these particles that would be detected by the detector over here, it's going to be 70, 72, and 74, three detections. These are your molecular ion, and I told you that they are labeled using the letter M. There's M. This is M plus 2 because it's I mean, this was 70, this is 70, 72, so that's m plus 2. This is 74, so that's m plus 4. Anyways, the relative heights are going to be 9 ratio 6 ratio 1, and they show you the relative abundance of these particles. And then you will be getting these fragments. Now, remember, the fragments have nothing to do with the molecular ion. I mean, their ratios, uh, because you don't know how much fragmentation is happening. Maybe no fragments are formed, like the ionization chamber is not breaking the molecule, so there would be absolutely no fragments. So don't compare the ratio of the molecular ion with the fragments. But if there are fragments formed, uh, the chlorine ion with 35 mass is going to be it's going to have 3 times the probability of getting chlorine 37. Okay, is this clear? Karmala, is this clear? The last thing, Ali, is this clear?
Yes, sir.
Actually, now the importance of that was that I told you that there would be different molecules that are going to have chlorines in them. And based on the mass spectroscopy, for example, if you have this molecule, which is CH2Cl2, there would be a molecular ion, which is going to be this one, that the molecule remains intact but ionizes. And there would be these tiny fragments that would be formed as well, where the molecule breaks down into tiny pieces. So you'll be getting these fragments over here. So you'll be getting a bunch of fragments. But we are interested in the molecular ion, which is CH2Cl2 plus. Now, in the same way, we calculate the probabilities. Now, carbon and hydrogen, they don't have a lot of isotopes. It's only chlorine. The variation is happening because of chlorine, because chlorine is 35 and chlorine is 37. Carbon and hydrogen have isotopes, but they are very, 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 very rare. Uh, so most of the detection and the differences, I mean, you get 3 different peaks. Why? Because in the molecule, both could be Cl35. So the mass comes out to be 84. And the second version is that the mass of the particle will be different. Why? Because one of them would be 35 and the other one is 37. So that would give you 86. Or both of them are 37. So that would give you 88. And the probabilities of getting these relative heights would be exactly the same, the one that we calculated above. Both CL35, that's 9 by 16. One of them as 35, the other one is 37, that's 6 by 16. And both of them as 37, that's 1 by 16. So your ratio comes out to be 9 ratio 6 ratio 1. Your molecular ion peaks are exactly the same. So whenever you do a random mass spectroscopy, you don't know what the molecule is. You'll get this type of diagram. Okay? I mean the upper calculations, ignore that. You'll get a bunch of fragments, lots of lines, lots of detections at different mass values, and there would be these molecular ion peaks, the biggest peaks, the heaviest peaks, 84, 86, 88. If you get 3 peaks, and if the ratio comes out to be 9 ratio 6 ratio 1, that indicates that the molecule has 2 chlorine atoms. So I'm going to summarize this that so the summary is whenever you look at a mass spectrum, if a molecule has one Cl, so if it has one Cl atom, then there's going to be M and M plus 2 peaks, and they would have a ratio of 3 ratio 1, like one Cl. So, I mean, if example is if you have a molecule of CH3Cl, now you're going to get 2 peaks because Cl could be 35 or it could be 37. So this one would be either you're going to have an M peak or an M plus 2 peak. M peak would come at this is 15 plus 35, that's 50. And the M plus 2 peak would be because of Cl37. That would give you 52. So you're going to get 2 detections. That either the Cl is 35 or this Cl is 37. So you'll be getting 2 detections at 50 and 52. And the relative heights would be that the probability of getting Cl as 35, that's 75%. And the probability of getting Cl as 37, that's 25%. So in that way, the ratio of the m plus 2 heights would be 3:1. So that's point number one. Point number two is if the molecule has two Cls. So what's going to happen in that is कि वही example जो CH2Cl2 की थी, that you're going to have m plus 2 and also m plus 4 peaks. The peaks would be at, like in this case, it would be 84, 86, and 88. And the relative heights would be, probability of getting this is 9/16. The other one is 6/16. And this one is 1/16. So those are going to be your relative heights of the, and let me write that down over here. So the m plus 2 and m plus 4 peaks would have a relative height of 9:6:1. Okay, is this clear? Aisha, is this clear? Ariba, is this clear?
Yes, sir.
अच्छा मैं अगला एक्सप्लेन करूँ उसमें फिर और क्लियर होगा ठीक है नाउ आई एम Ali, is this clear? Sarah, is this clear?
Yes, sir.
अच्छा, so now let's do the same thing with bromine now, because bromine also has two isotopes and they're very abundant. Like there is bromine 79 and there is bromine 81. The relative atomic mass of bromine is 80 because 79. I mean, there is no bromine that is 80 actually. There's either 79 or 81. But since they have equal probability, which is 50%, 50%. So if you do a mass spectrum of a molecule that contains bromine, okay, let's start with Br2 plus 1. Let's say I ionize Br2 plus 1. Like I add a Br2 molecule in the ionization chamber. A beam of particles, charged particles, is formed. The beam contains molecular ion, which is Br2, which is Br2 plus 1. So that's a molecular ion. Or it might break down into fragments. The fragments would be a bromine atom, which is also going to get ionized, and that's going to be my fragment. I said then there's going to be a magnetic field, and the particles are going to get deflected by the magnetic field. So you're going to get 5 different deflections again. So there would be so there would be 5 different deflections and detections at different points. The first one is the heaviest one. That's the lightest. It's going to be Br2 plus 1. Why? Because both of them would be 81. 81 and 81. So it's going to be Br 81. And the other one is also Br 81. So what's the probability? The probability of getting Br 81 is 1/2. And the other one is also Br 81. So that's also 1/2. So the total probability would be it's going to be 1/4. I said, what about the next one? Let's say you're getting Br2 plus 1 again. But now the mass is, as I did not write the mass, this one would be 162. This one is coming out to be 160. So how can you get 160 if one is 79 and the other one is 81? Or the first one is 81 and the second one is Br 79. So you have two options uh, to get 162. The probability would be It's going to be half into half. I mean, this is half, and this is also half. And when you get OR, that's plus, so it's going to be half into half again. So it's half into half again. And if you sum this up, it's going to come out to be 2 by 4. So what about the third one, which is you can also get BR as you can also get BR2 as 158. That can be like you have BR2 plus 1 ion getting detected, and it's BR which is 79, and the other one is also 79. So now it's going to be half into half again, and that gives you 1 by 4 again. Okay, so remember the probabilities of getting bromine uh, was 50-50%. That's 1 by 2 and 1 by 2. That's equal probability. Like out of two events, there's one chance of getting this one chance of getting this one. So that's 50-50%. So I've calculated all my probabilities, and the relative ratio of the probabilities is that it's coming out to be 1 ratio 2 ratio 1. That means that if I detect 4 particles, then, and I'm talking about the molecular ion, if I detect 4 particles of molecular ions, 2 of them would be the 160 Br2 plus 1. One of them would be the 162 one, and the other one would be the 158 one. So that's the relative height that I'm going to get. So we can plot a graph of mass to charge ratio. This is 162, 160, and you have 158. So you're getting detections at these 3 points, and the relative heights are 1 ratio 2 ratio 2 ratio 1. And then you would be getting these fragments as well. The fragments, as you already know, you might be getting a fragment of 81, and you might be getting a fragment of 79. So there are going to be detections at 79 and 81, which are the fragments that are forming. But the probability of getting the fragments would be equal, because getting 79 and 81, they have equal probabilities. ठीक है, is this clear? Abu Rana, clear? Ariba, Sara?
Yes.
Yes, sir.
So equal probabilities.
Yes, sir. The
अच्छा, so
fragments will be equal.
yes, because getting bromine 79 or 81, that's equal probability, right? I mean, when you ionize bromine, the bromine atom is the only fragment that you're going to get. Okay, the other one would be the molecular ion. So, I mean, bromine has 2 masses. It's either 79 or 81, and the probability of getting both of them, it's equal. So the relative abundance or the height was the relative abundance of the particles that the detector is detecting. So that's the percentage abundance. It's going to be the same. I said now how are you going to use this? In the same way, like if you have a molecule and you're doing mass spectrum, and let's say there's a molecule of there's this molecule. Now, and you do a mass spectroscopy of this molecule. So it's the molecular ion that you're going to get is CH, Br2, and there is COOH. Now, you can figure out the mass. I mean, this is your molecular ion. It would ionize. And this is a particle that you're going to detect in the mass spectroscopy after deflection. But the particle is going to have 3 different masses. It would either have a mass of, for this you would, I mean, COH is 45, 45 plus 13 is 50, 58. Okay, just 1 second. So it's 58. So 58 plus. Now getting both bromines as 79, that would be 79 plus 79, and that gives me. So you're going to get three different masses for this. Both Br 79 and 79. So that is going to have a mass of 160. Then one of the Br is 81, and the other is 79. Not 160, it's going to be 216. And the other is Br 79. Now the mass that you're going to get is going to be two more. That's going to be 218. And if both bromines in the molecule are 81, then the mass that you're going to get is going to be 220. Okay, so the point is कि ये जो आपका molecular ion है, it's going to have three different masses. So जब इसकी deflection होगी ना, when you pass it, you make it into a beam and you deflect it through a magnetic field. Not talking about the fragments. The molecular ion is going to have it's going to have three different deflections, and three particles of different masses would be detected. There would be a 220, there would be a 218, and there's going to be a 216 that would be detected. Okay, and the ratio in which they're going to be detected is the probability of getting both bromines as 79. That's 1 by 2. If one of the bromine is 81, that's 2 by 4. And the probability of getting both as 81, that's also 1 by 4. So if you do the mass spectrum of this substance, so the highest peaks, the molecular ion peaks, that would be detections at 216, at 218, and at 220, which is the M peak. Then you have the M plus 2 peak, and then you have the M plus 4 peak. So the relative heights would be 1:2:1. That's the probability of. So for every four particles of the molecular ion that are detected, one of them would be 216, two of them would be 218, and one of them would be 220. That would be the relative abundance. And then you would get lots and lots of fragments, lots and lots of fragments obtained. Like the molecule can break down into tiny, tiny pieces. So we don't care. We're not caring about the fragments right now. We have no concern for the fragments at the moment. So these would be your fragments. Like while doing this, the molecular ion could break down into smaller, tinier pieces. So you would get lots and lots of combination. Like the OH could break off, the CO could break off, the CBr could break off, the CC bonds could break off. So lots of things can happen. Okay, so is this clear? Aisha, is this clear? Abu Rera?
Yes.
Ara? Ariba, ये clear है?
Yes, sir.
Yes, sir.
अच्छा, तो ये पहली चीज है. इससे इन्फॉर्मेशन आपको क्या मिली? एक सेकंड, मैं बोर्ड मेरा पता नहीं कहाँ चला गया. अच्छा, so this is the first thing, ठीक है, you have to remember. Okay, how do you figure out that there are two bromines or two chlorines in a molecule? But if you get this thing, just this thing, and you have no idea what the molecule is, so by just looking at the molecular ion peaks, M plus 2, M plus 4, you'll see that the ratio is 1:2:1. So that is an indication that the molecule has two bromines. Vice versa, if the molecule has one bromine, then it's going to have equal height. Okay, because either bromine could be 79 or 81. So let's, Ali, is this clear? कोई question तो नहीं है?
No, sir.
अच्छा, let's just summarize all of it. ठीक है. So if 2 CLs, that's 9:6:1. There's M, there's M plus 2, and there is M plus 4. If there is 1 CL, then there is only M plus 2. I mean, there's no M plus 4 because 1 CL can have only one variation, which is it's either 35 or 37. So the mass could only differ by 2, not by 4. If there are 2 bromines, okay, let me. Achha, vice versa if. Achha, if there are two bromines, then the ratio of the M plus 2 and M plus 4 peak would be 1:2:4. Not 2:4, but 1:2:1. And if there are there's only a single bromine, then it's going to be 1:1. Okay, equal probability. So you might get an M peak if there's one bromine. Like if a molecule has one bromine only. So the molecular ion hoga, that's going to be detected. That's going to be the heaviest one. So it's going to have two masses only. It's either M or M plus 2. CH3 is 15. 15 plus 79 is 84. So you're going to get a detection at 84, or you might get a detection at, if bromine is 81, that would be 86. And both of them have equal probability because getting 79 and 81, that they have equal probability. ठीक है, ये क्लियर है सारों को?
Yes, sir.
Yes, sir.
अच्छा, फिर अब mass spectrum से ना, what other, by just looking at this, I mean, you get this random fragmentation pattern, ठीक है? मतलब एक random molecule को you put it in a ionization chamber, you start detecting the particles and you start deflecting the particles, heavy particles, light particles, ठीक है? उसकी जो deflection है, you can calibrate it to figure out the mass of the particle. So by looking at it, you can detect the number of chlorines and the number of bromines. Another thing that you could do is, and that is, you can detect the number of carbon atoms in the molecule. Okay? So if a molecule has a mass, if a particle has a mass of 84, अब आपको कोई आइडिया नहीं है कि उसके अंदर कितने कार्बन हैं, कितने ऑक्सीजन हैं, कितने नाइट्रोजन हैं. क्लोरीन और ब्रोमीन का तो आइडिया हो जाएगा, but you won't be able to figure out how many carbons does it have. If something has a mass of 220, how do you figure out how many carbons it has or how many oxygens it has? So another thing that is helpful is that you can find the number of carbon atoms through mass spectroscopy. And there's a formula for finding the number of carbon atoms, and that is 100 over 1.1 into the m plus 1 height divided by the m height. और इसका बता दो, explanation हम फिर next class में करेंगे. Carbon has two isotopes. Remember, I told you that apart from chlorine and bromine, other isotopes are kind of very rare. But carbon's isotopes are not extremely rare. They do exist. Carbon is usually 12, and the probability of getting carbon 12 is 98.9%. Like every time you see carbon, 98.9% of the chance is that it's going to be 12. And if it's carbon 13, the probability is approximately 1.1%. Okay, so carbon does have isotopes, but the probability is much lower. So by just looking at the mass spectrum, you can figure out the number of carbon atoms. लेकिन वो फिर अभी खैर इतना टाइम नहीं है. So we'll study this, discuss this. How do you figure out the number of carbon atoms? ये मुझे तो पिछला clear है सारों को. Ariba, is this clear? Isa,
जी सर.
ठीक है अली, कोई question नहीं है? चलो ठीक है, ये फिर ना नंबर ऑफ कार्बन एटम्स कल फिर हम डिस्कस करते हैं, हाउ डू यू फिगर आउट द नंबर ऑफ कार्बन एटम्स इन अ मॉलिक्यूल, ठीक है?
ओके सर, ओके, अल्लाह हाफिज़।
ओके।